Good morning, sir.
Mm. Today, I don't want us to wait at all so that we start incurring any challenges again. Okay, so I'm going straight. Last time we talked about resistor color codes, and then uh, we went ahead to talk about inductance. Oh. So we talked about inductance, lumped and distributed elements. So we talked about types of sources, if I remember, independent and dependent sources. We talked about that. Ideal and practical sources. Then we talked about ideal voltage source, meaning it is this how it's supposed to be, but this is what is actually the presentation, the representation. Okay. So the voltage, when you say voltage source, that means that we are increasing the voltage and maintaining the current. So look at that. So this V1 plus V2, that gives you the voltage. So if you have a lot of cells series, arranged in series, you are increasing the voltage, but the current will be the same. So that is a voltage source. Then this is how it is presented. You see that? So which means that if you are increasing the voltage, it means that it has resistances, so internal resistances. But on the ideal situation, you will not see these resistances. You will not see that there are internal resistances. You will only see V1. Let's just take like a battery. You see the battery, you think that, oh, that's a battery, that's only a voltage source. No, actually, practically, what happens is that there are internal resistances cell, from each cell that produces the battery or that produces the voltage, right? Each cell has internal resistance, but on the outside, we don't value or we don't regard it. So that is why this is the practical thing that is happening inside the battery. But on the ideal situation, you only see it as this. See, you only see it as this, as a voltage source. You only see it like this. You don't see the resistors added to it as the internal resistance. Then ideal voltage source connected in parallel. Look at that. So you don't see any battery, any resistance connected to it. You see. So the EMF, the V1 is equal to V2 and is equal to the V. So when you connect voltages, the cells in parallel, you are maintain the same voltage throughout. If it is 2 volts battery you have connected it in parallel, what you are doing is that you are increasing the current. That means you want to have a high current, and then you want to maintain the same voltage. So this is how come, you see, normally at the cell site, you see, normally at the cell site, you see that they have uh, 12 volt, 12 volt, 12 volt, 12 volt. And most of the times you see them connected in parallel. That means that they want a very high current. You see, sometimes you see them connected uh, in series and parallel. So if it is 12 volts and you put another 12 volts in series with it, that means that we are getting 24 volts. When they get it, that means they were not having one battery as 24 volts battery. So they have to cascade by adding in series. So they'll get one 12 volts plus another 12 volts, making 24 volts. Then they'll be putting that 24 in parallel. That means that if uh, one 12 volt produces, let's say, it produces a current of 13 amps. Let's just imagine it produces a current of 13 amps. Then you add another voltage, another battery in parallel, in series with it, it will still maintain the 13 amps, but the voltage will now become 24 volts. That 24 volt that we have now, when you increase it in parallel, you put it in parallel, now you get 4 12 volts. Two are in series and then they are in parallel to each other. So now the current will increase to 26 amps. You see that? You now have 24 volts with 26 amps. That will become uh, more powerful. So we have that. So where am I now? I'll come back. Okay, so that's where we are now. Aha, now you see. So practical voltage was connected in parallel. See, they are all connected in parallel. See, so I will be equal to V1 over R1, which is an internal resistance. These things are these things are for calculation sake. So I2 will also be V2 over R2 because they have internal resistances. So you see, that's what you are doing here. So now that we are summing the two of them up, that means the current at this point, right, will be equal to I1 plus I2. So this becomes, and I1, look at it. Now internal resistance becomes, when you put two resistors in parallel, you can calculate for that, two resistors in parallel. You see that R is R1 plus R1 times R2 over R1 plus R2. Okay, so that becomes the internal resistance for the two uh, cells in parallel. Okay, so I did current source now. Look at the current source. When current sources are connected in parallel, like I said, when current sources are connected in parallel, we are going to get summation of the individual currents. Summation of the individual currents to get what? The current at the output. So this is the equivalent representation of current sources connected in parallel. That one, you see the resistance. The resistance is not connected in series with the input or with the source. Rather, it is in parallel with the source. So this is what you get. I is equal to I1 plus I2. And then R is in parallel. So you get R1 plus R1 times R2 over R1 plus R2. Please, are you following?
Yeah, we are following, sir.
Don't just connect and isolate yourself. Oh. So source transformation. So a current source or a voltage source drives current through its load resistance, and the magnitude of the current depends on the value of the load. I think I said this the last time. Consider a practical voltage source and a practical current source connected to the same load resistance. Load resistance is the connected appliance, okay, something that will utilize the energy. So I think we said this already. So the voltage source, this is a voltage source. The energy supplied by the voltage source, okay, is equal to the voltage drop. Voltage drop is the amount of voltage utilized by the load. The amount of energy utilized by the load is called the source. And that will be equal to voltage drop is equal to the current it received or the current it pulled times its resistance. So Vs equal to Is times Ri or RL. Okay, so this is it. R1's in figure represents the internal resistance of the voltage source, that's Vs, and current source, that is Is. Two sources are said to be identical when they produce identical terminal voltages, that is VL, and load current, that is IL. I mean, you understand this. The current in figure represents a practical voltage source and a practical current source, respectively. So you can see that. You can see that here. So voltage source and a current source with load connected to both the sources. The terminal voltage, as VL, and load current cross their terminals are same. Across their terminals are the same. Hence, the practical voltage source and practical current source shown in the dotted box of figure are equal. The two equivalent sources should also provide the same open circuit voltage and short circuit current. So you see that. Look at that. You see, we have IL as a short circuit current. Vs, okay, is equal to R plus RL. And we said that Vs is the voltage source, right? This is a short circuit current. Then the open circuit voltage, open circuit current will become R, because it is open circuit, there's no voltage across. So you have R, which is a resistance, divided by R plus RL. Therefore, we can say that IL is equal to Vs over R plus RL. The reason being that Vs, the R here is automatically part of the Vs. You remember, we said a practical view, you will see that we have internal resistance, okay, will be added to the source voltage. And then the load resistor will be added to the internal load. So we now have Vs over R. R that you see is a total resistance. So now we are going to RLC parameters. We have resistance, inductance, capacitance to calculate for. So resistance. Resistance is the property of a circuit element which opposes the flow of electric current, and in doing so, convert electrical energy into heat energy. It is the proportionality factor in Ohm's law relating voltage and current. Ohm's law states that the voltage drop across a conductor is given of a given length, and area of cross-section is directly proportional to the current flowing through it. So resistance practically is the impedance for current. Okay, it's something that regulates the flow of current or set a limit for the flow of current. So we can say V is directly proportional to resistance, and we can also say V is directly proportional to current, and then current is voltage over resistance. Where the reciprocal of resistance is called conductance. Why conductance being the reciprocal of resistance? Resistance is opposition. Conductance is permeability. Okay, so whilst resistance is trying to limit the flow of current, conductance is rather opening the way for current to move. So if current is inversely proportional to resistance, it means that current will be directly proportional to resistance. That is why we have I equal to GV. I equal to GV, right? And then I will be equal to V over R, because current is inversely proportional to resistance. The unit of resistance is ohm, and the unit of conductance is mho, which is Siemens. When current flows through any resistive material, heat is generated by the collision of electrons with other atomic particles. The power absorbed by the resistor is converted to heat and is given by the expression power. Remember, power. Power is equal to VI or IV. And power can also be equal to I square R. It is not I2R, I square R. Where I is a resistor in amps. I is a current in amps, okay? And voltage is the voltage across the resistor in volts. So I is the current of the resistor in amps, okay? It's current, it's not resistor. Philip,
Sir, please, this formula I don't understand. The one we have I is equal to V over R equals to GV.
that's what I just explained though. I was in the explanation.
So why the I and the V are down? Down, that's why I don't know.
I'm coming in. Oh, why? I nearly left the meeting. Okay. So, you said I equal to V over R. Is that what you're talking about? Philip,
Yes, sir.
I equal to V over R, right?
Mm-hmm.
So, for Ohm's law,
Sir,
V,
sir, please, sir, I want to know whether the formula is correct because the G um is it the V over R is equal to GV.
is it what?
So the equal to sign is 2 over there. So I
Yes.
want to know, I want to know how it is.
Okay, so let me explain it to you.
Okay.
I equal to V over R. Do you know that one already?
Okay. Yeah, I know that one already.
And the same I is equal to GV.
Ah, okay. Okay. The same I is equal to GV. Okay. Okay.
Yes.
Okay. Okay, sir. I get it.
Can we go on?
Yes, sir.
Yes.
Yes, sir, we can go on. I understand it.
Okay. Now you people, you said you are integration and differentiation masters, right? So let's start. When the current flows through any resistive material, heat is generated by the collision of electrons with other atomic particles. The power absorbed by the resistor is converted to heat and is given by the expression power equal to VI, and it's also equal to I squared R, where I is the resistor's current in amps and V is the voltage across the resistor in volts. Energy lost in the resistor in time is given by the expression power. Oh, sorry, energy is W, so it's not power. Okay, it's energy or work done. Okay, please don't associate this one to power. This is not power. So work done or energy is from zero as time progresses from zero to tile, where tile is time or a certain time. You understand? So if I take it from 0 to 2, that means that from 0 seconds to 2 seconds, right? Power power dt. Okay, power dt. So that means the integral of power with respect to time. So that pt is equal to I squared rt. I squared r is power, please note. I squared r is power. So then we'll be having v squared divided by r, which is the same as what? Power. You understand? Okay. Now let's move ahead and see. Inductance. Inductance is a property. No, but we're supposed to have some calculation here. Let's go on. Inductance is the property of a material by virtue of which it opposes any change of magnitude and direction of electric current passing through conductor. Inductance is a property of a material in virtue of which it opposes any change of magnitude and direction of electric current passing through a conductor. A wire of certain length, when twisted into a coil, becomes a basic conductor. A change in the magnitude of the current changes the magnetic or the electromagnetic field. Increase in current expands the field, and decrease in current reduces it. A change in current produces change in the magnetic field. This produces a voltage across the coil, according to Faraday's law of electromagnetic induction. So an inductor is an electronic device that converts electric current or current into magnetic field, okay, or electromagnetic field, let's say so. So that increase in current is directly proportional to increase in magnetic field, and reduction in the current reduces the magnetic field. I think that is okay. So inductance voltage, which is also referred to as L, L di dt, L di dt, which means that inductance will increase depending on increase in current with regards to time. V equal to is voltage across inductor in volts. I is current through inductor in amps. Okay. Di equal to 1 over L V dt. 1 over L V dt. So this is the formula. So integrating both sides. So we are now integrating I or dt, and then we equate it to I over L integral of voltage. So power absorbed by the inductor will become P equal to VI, which is VI, which is equal to LI. Energy absorbed energy stored by the inductor. Remember, you see this, you have seen this before. And this time it is what? In the inductor. So you have now L. Okay, at first it was resistor. Resistor behaves like inductor. So that is why this equation is almost the same as what you have seen already. When we get a capacitance, you see that it will change a little. So please observe this. Integral of Li with respect to dt, di dt, where dt equal to Li squared over 2. So in a nutshell, the power absorbed by the inductor, or let's say the energy absorbed by the inductor, the energy absorbed by the inductor equal to Li squared divided by 2. So in summary, we have V equal to L di dt. The induced voltage across an inductor is 0 if the current through it is constant. Yes, of course, because it's based on change in current. Okay, change in the direction of the current. So if the current is constant, right, the voltage across the inductor will be 0. That means an inductor acts as short circuit to DC. You see that? So when you connect an inductor across a DC voltage, it will act as a short circuit. This is interesting, you understand? For minute change in current with zero time, like as in dt equal to 0, gives an infinite voltage across the inductor, which is physically not at all feasible. This means that you cannot say that within a minute, right? Within a minute, you have currents changing so fast that the time for the change will be 0. They say it is physically not feasible. Definitely some time will pass, okay, whilst the current is changing. Some time will pass. So in an inductor, the current cannot change abruptly. The current cannot change abruptly. It will take some time. An inductor behaves as open circuit just after switching across DC voltage. The inductor can store finite amount of energy. That means it is determined. Okay, so that's how we can rate inductors like the way we rate resistors. It has its tolerance, it has its limits. Even if the voltage across the inductor is 0, still we have the limits for the inductor. A pure inductor never dissipates energy. It only stores it. Hence, it is also called as a non-dissipative passive element. However, physical inductor dissipates power due to internal resistors. So which means that when we referring to dissipation of energy, that means that it should be passing some current. Okay, it should be passing some current. That's physically, but ideally, the inductor is not supposed to pass current. Just as they were referring to uh, resistors resistors opposing current and then changes the energy to heat energy. Meanwhile, a resistor will only produce heat if it is overutilized or works beyond its resistance. Because of that, when you use the right resistor for the right circuit, it will not generate heat. It will work perfectly without generating heat. The same way, if you are using an inductor, okay, you are using it rightly or the right value for the inductor for the circuit, it will not be emitting current, okay, or it will not be generating power across it. It will rather change all the power into electromagnetic field. That electromagnetic field is what is used in the industry for a lot of industrial processes. So that the more the current, the more the electromagnetic field. If we keep increasing the current beyond the rating of the inductor, or comparing to the cross-sectional area of the cable and the number of turns, if you increase the current beyond that, now it will not be able to change all the current into its equivalent uh, electromagnetic field. So some current will seep through. You see that? Okay. Increase in current expands the field, and decrease in current reduces it. I think we've done here already. So that's what you said here. See, a pure inductor never dissipates energy. It only stores it. Storing it is what is producing the electromagnetic field. Hence, it is also called as a non-dissipative passive element. Mhm. Okay, so a pure inductor never dissipates energy. It only stores it. Hence, it's also called it's also known as a non-dissipative passive element. However, physical inductor dissipates power due to internal resistances. You see that due to internal resistance, it will definitely dissipate some power because of imperfection. So, example, the current in a 2 Henry, okay, inductors are measured in Henry. 2 Henry inductor raises at a rate of 2 amps per second. Find the voltage across the inductor. The energy stored in the magnetic field after 2 seconds. So V equal to L di dt. In this case, we are given the inductor to be 2 Henry, remember, and then the current, a change in current with regard to time. Change in current with regards to time, that is 2A per second or 2 amps per second. So you see di dt the I dt becomes what? 2 amps per second. So we have 2 times 2, which becomes what? 4 volts. They were asking for energy, okay, or voltage. So find the voltage. So the voltage becomes 4 volts. Then we can also say, use this formula. We can continue by saying 4 volts, 4 volts, whereby W, the energy, is equal to 1 over 2 Li squared. 1 over 2 Li squared. So we have the L inductor to be 2. Then the I, the 4 volts, the voltage or the current is 4 squared, which will give us 16 joule. That is the energy. Because here we should find the voltage across the inductor. Then the energy stored in the magnetic field at 2 seconds. Hmm. People, please, do you understand this? Hello?
Yes, sir.
Okay, okay. We
It's
are not
not
even
quite.
clear. Are you understanding this?
No, sir. This part didn't sit well to me in
Mm-hmm.
my memory.
Let's go back and take the W. That's the energy. You see, the energy, say W equal to what? V squared over R dt over RT. Now that's this for resistance. Let's talk about inductance. The I equal to 1 over L V dt. You see that? 1 over L V dt. So and look here too. Li squared over 2. You see that? Li squared over 2. Then what is, you see, energy? Energy stored by the inductor. All right, energy stored by the inductor is Li squared over 2. and V equal to L di dt. Please, I hope you are noting it. Then here comes the question. You see that? So we were able to use this to generate the voltage. After generating the voltage, we got 4 volts, right? Then we are now using the same to generate the energy, right? Which is what? 1 over L. 1 over, what is it? This is it. You see, it is Li squared over 2. Li squared over 2. Of course, Li squared over 2 is the same as 1 over 2 Li squared. It's the same thing, okay? So, this you can say that it is Li squared over 2. Li squared over 2. And we found we have the value of L to be 2. Okay? And then that means we have to find I. Let's go back. And you know, I is proportional to voltage. Current is proportional to voltage. So where we had the voltage, you see, where we have the voltage, wherever in this, oh, my battery is low. Please, okay, wait, I'm coming. Oh. Okay. Okay, so wherever we see V, we can equally put I there because I is directly proportional to voltage. Okay, so already they gave us I to be 2 amps per second. Okay, 2 amps per second. That's the I that was given. And we calculated for the V, we got 4 volts, right? And I is directly proportional to V. So in this formula, look at this formula. The voltage we calculated for, right? And then the inductance we were given. Because I squared, I is proportional to V, we'll have 4 exponent 2, okay? Which will give us 16 joule. This 1 over 2 will cancel these 2 out, leaving 4 exponent 2. 4 exponent 2 will give you 16 joule. So that is it. I hope you understand it.
Yes, sir.
Okay. Then we move on to capacitance. The capacitor consists of 2 metallic surfaces or conducting surfaces separated by a dielectric medium. A. It is a circuit element which is capable of storing electrical energy in its electric field. B. Capacitance is its capacity to store electric energy. Capacitance is the proportionality constant relating the change on the conducting plates to the potential. So charge on the capacitor, which is Q, okay? And then we know Q equal to CV, which is what? Capacitance times voltage, where C is the capacitance in farad. Okay, if charge, which is Q, in coulombs, and V is the potential difference across the capacitor in volts. So we keep it in mind that Q equal to CV. Q is a charge, C is the capacitance, and V is the voltage or potential difference across the two plates. So current flowing through the capacitor. We already know that charges are stored. Okay, as current flows through the capacitor, charges are stored. So current is equal to change in current, change in charge per change in time. Okay, change in charge per change in time. So we can equally say that the capacitance or current will be equal to capacitance times change in voltage per change in time, because charge is equal to capacitance times voltage. You see that? So current will be equal to capacitance times change in voltage per change in time. Then it is easy to say I equal to C dV dt, which is making sense. The capacitance of a capacitor depends on the dielectric material. Please note this. The capacitance depends on the dielectric material, or the size of the capacitor depends on, or sorry, not even that. The charge of the capacitor depends on the dielectric material and the physical dimensions. Okay, so for a parallel plate capacitor, the capacitance will become, the capacitance will be equal to the cross-sectional area. No, this epsilon A. Okay, epsilon A. Epsilon A is the absolute permittivity of medium. Okay, absolute permittivity of a medium. Of free space is R. Okay, so this is epsilon A. It's actually supposed to be epsilon naught A. Okay, so this will be equal to epsilon naught, yes, epsilon naught times epsilon R times A divided by D, okay, where A is the area. A is the area or cross-sectional area of the material, okay. Then D is a separation between the plates as a dielectric material. And epsilon naught, this epsilon is supposed to be epsilon naught. Epsilon naught is the absolute permittivity of medium. Okay. Okay, so you say epsilon is the absolute permittivity of a medium, any medium at all. Then epsilon naught is the absolute permittivity of free space. Please note the difference. Epsilon is the absolute permittivity of any medium at all. Then epsilon naught with a 0 is when we are rating permittivity, permeability of free space. Okay, that becomes epsilon naught. Then epsilon r is the relative permeability of medium. Okay. So in this case, we can say that capacitance or current is change in capacitance or change in charge per change in time, which will be equal to capacitance times dV dt. We know this already. All what you are doing is to find the dielectric material. Okay, so dV dt is equal to I over C. I think we should understand this. V equal to 1 over C integral of I dt. The power absorbed by the capacitor is P equal to VI, which is also equal to VC dV dt. Energy stored in the capacitor is W, right? Which is integral of P dt, which is P is power, and Vc, our integral of Vc dt, dV dt. Okay. So we can confidently say the energy stored in a capacitor is equal to C, right? C integral of V dV. And this will become 1 over 2 C V squared. So, my people, you see this one, the end of the formula, this one is what you should keep. Okay. We are not doing mathematics here. So keep these ones, the end of it. I will not go and ask you to be doing integration to come and produce. No, that's not my job. Okay, we are interested in the results here. So remember this formula. W equal to 1 over 2 CV squared. Energy is stored in the electric field set up by the voltage across a capacitor, which is 1 over 2 CV squared. Conclusion. The current in a capacitor is 0. Yes, there will not be current in a capacitor. If the voltage across it is constant, I think you should understand that. That means the capacitor acts as an open circuit to DC. You understand it? A small change in voltage across a capacitor within 0 time gives an infinite current through the capacitor, which is physically impossible. By the way, inductor's own is the same for the capacitor. In a fixed capacitor, the voltage cannot change abruptly. The capacitor behaves as a short circuit just after switching across DC voltage. Meanwhile, the inductor, the inductor behaves as an open circuit. Okay. Here it operates as a short circuit rather. The capacitor can store infinite amount of energy even if the current through it is zero. You see that? A pure capacitor never dissipates energy but only stores it, hence it is called non-dissipative element. I don't want to take Ketchup's law today. When are we supposed to end?
So 11:15.
11:15.
Yes,
I
sir.
don't want to take Ketchup's law today because we have enough today. I wish you go and go through it, read over it to understand it better. If I take Ketchup's law, I'm going to add more load to you. But if you want us to continue, I'll continue for you.
So I think
Say again.
we can end here. We
I
can
think
end
we should
here.
leave it here. Okay.
Yes.
Please go over, read it. You will understand it better after you take your time and go through. All right. So, have you gotten your results?
So not yet.
You get it. Okay. All right, guys, you did very well. Most of you did
Oh, okay,
very
sir.
well.
Thank you.
Mm,
Mm.
you did very well. There was one. You have one lady among you, right?
Yes,
Yes,
yes.
please.
Hey, Jack.
I'm here.
Respect, respect, respect. However you did it, keep it up, okay? Did you hear
Yes,
that?
please. Yes, please.
Okay, so we are yet to see your results. I hope what I
Oh,
presented to them, that's exactly what you receive.
please,
Okay,
what's the least mark? What's the least grade?
I cannot remember. It's I presented it long ago.
Hey. Hmm.
I presented long ago. You know, when you present results, it will go through moderation. Now they will have to sit up on it and then to do some analysis with it and find out about how the exams went. Was there any form of exam or practice and all that? So they will consider all these things before they publish the results. They don't just publish it like that. So
So if there's exam or practice, it means that they'll invite you, the candidate, right?
it's likely they will invite you if they detect that there was exam or practice. But that will not be at your level. At my level, I will detect that there was exam or practice.
Oh, okay.
And when it is given to uh, the moderation board, they will now take it on a higher level to check if the questions were leaked, for example. You understand? They will check how come that you conduct examination, everybody will get 90%. How possible? You understand it? So that does not become something for the lecturer to be able to determine. It's for the board to doubt the integrity of the examination. You understand it? So in every examination, definitely some people get a very high mark, some people get a very low mark. So there'll be a form of a normal curve. So that's what they will sit to observe. If everybody gets a very high mark, there's a problem. If everybody gets a very low mark, there's a problem. It means the questions were not set to standard. There are three conditions here. The questions were too difficult. The questions were too low. And there was examination malpractice. These are the two dangers that may come up. So in every examination, it's expected that a group of students will perform very well, a group of students will perform quite low, and a group of students will be average, in the average region. So this is normal. But when you conduct examination, at least, if nothing at all, some should be average and some should be high. Or some should be low and some should be average. You understand? But if all of them are high, as in from 85% to 100%, there's a problem. If all of them are low, let's say from 0 to 25%, there's a problem. And if all are average to, that is normal. So let's wait for the outcome of the board and you will see. But from my side, that will be for me to answer if it happens like that. From my side, you have done well. You have done well, and I can defend whatever you have done. Okay. Uh-huh.
Thank you, sir.
You're welcome. So later.
Okay.
So I can leave, right?
Yes, sir. Thank you.
Okay. Bye-bye.